Hey everyone, I am starting a series on how AI works, and I want this to be a fun, gentle, accessible introduction to the topic. If you know anyone who you think just might be interested in getting a nice, gentle introduction to how this stuff works at all, send them a link to the channel. I'd love to see them here. Okay, let's dive into tokenization and what is a token and why tokens matter at all. Okay, so the topic we are getting into for this very first video is tokens and tokenization. What are tokens? You might have heard this term token in a couple different places. You may have heard that AI models do next token prediction. So we know that they're predicting the next token. If you've looked at the billing page of these AI services, you'll know that they charge per token or per million tokens. So what are these tokens, right? I think when pinned down, a lot of people have a sort of fuzzy definition, and we're going to try to get to where we all have a more clear understanding of tokens. The other great thing about starting with tokens is it gives us some early wins around common questions that come up with AI models. Like, why can't ChatGPT count the number of R's in the word strawberry? I think it can now, by the way, but it couldn't for a while. But like, why couldn't it, you know? And the reason for this actually has to do with tokens. So by virtue of learning about tokens, we're going to learn the answer to a bunch of other super interesting questions about how AI works. Okay, let's dive in. Okay, so we know that for the model to be able to predict what comes next when it's given some text, it needs to have a finite list of things that it can pick from. And this ends up being the token list, or the vocabulary, so to speak, of the model. So when I first thought about this problem, I thought, well, it doesn't seem too hard. Why don't we just make each word its own token? So the available things the model can pick from when it's predicting the next token is every possible word. Right? Sounds good at like surface level, right? But it turns out this doesn't work well for a number of reasons. Think about it this way. Some words in the training data that gets fed to these models are only in the training data like once or twice. Think about some like rare words that Shakespeare might pull out of nowhere, or like certain very obscure, esoteric, like scientific terms that only show up once or twice in a science journal from 1750, right? If you make every word its own token, your list of available tokens the model can choose from ends up being too long. And it makes the prediction process more difficult for the model because it has so many different options to choose from when it's predicting the next token. There are other reasons why making every word its own token might not make the most sense. If you think about it this way, a lot of words share roots, right? And if you think about this word that I use as an example here, unbreakable. So unbreakable is comprised of a few parts, right? You've got this un prefix, you've got this break root, and then you've got this able suffix, right? And there are lots of words that have this break root, right? Breaker, breakup, breaking, just like run, runner, running, runs. And if you have a separate token entirely for all of those words, you end up like re-encoding a lot of meaning, like for that word break. Like that meaning of the word break gets duplicated across all those different tokens that had that word break in it. Whereas if you didn't do that approach, if you just had a token for break that got used in different places, then you'd be able to just encode the meaning of the word break in one place rather than in every single word that has the word break in it. Okay, so another downside of every word gets its own token is that this ends up being really bad if you put a word in your prompt that's like totally brand new, like a word the model has never seen before. If the way the vocab list for the model is that like, okay, every possible word gets its own token, and then you send it something that it's never seen before in the training data, it just will have no idea what to do with that like new word that you've put in. Okay. So then I thought, okay, well, why don't we what about the total opposite approach? Instead of each word getting its own token, what if just each letter of the alphabet was its own token? Okay. So for unbreakable, rather than having it be like one token, maybe just each character would be its own token. So instead of the model having to predict between a list of like millions and millions of vocab words, the model only ever has to predict what letter comes next. And that's a nice small range of options, right? The model's only picking between like 24 characters, not between a million different words. But it turns out that's not particularly efficient for other reasons. It's actually very difficult for the model to try to sort of compose meaning out of individual characters. It's actually shockingly possible. It does like work in sort of to a certain extent, but as of now, it's not particularly efficient, right? Instead of the model just having a token for cat, the model has to like build up meaning one letter after the other, C, then A, then T, and it ends up being inefficient. Now, it is the case that when a tokenizer is trained this way to just make each character its own token, that's when, if you ask the model how many R's are in the word strawberry, it would be able to get it right. So this is this famous problem, right, with large language models. I think it might be gone now in the latest versions of all the models, but certainly for a while, like if you asked an LLM to count the number of R's in the word strawberry, it would get it wrong. And it's easy to actually take the wrong thing away from this funny example of, oh, the AI can't even count the number of R's in the word strawberry. And my encouragement to you is to not read too much into this, besides keeping in mind that the way the model understands language and ingests and digests and processes language is fundamentally different from the way that we do. And as such, because I've really internalized that lesson, it's not actually surprising to me that the model, like that there are these little gotchas we can do with the model that to us seem so intuitive. But to the model, it wouldn't, because it's not actually processing the word as we're used to seeing it. It's processing tokens, which at the end of the day end up just being numbers. We're going to get to that. Okay. Now, I will also say, like, it's very tempting for people to underestimate the models because it gets some of these questions wrong. But there are other things about the way the model processes language and this tokenization process that make it so that it can do things that we cannot even come close to doing. The speed at which it can process certain things and things like that. Like, those are things that if you asked me to do some of the things AI can do, it'd be a big gotcha for me. I'd be fumbling around and stuttering, just like the model does when you ask it this simple question. Okay, so don't read too much into how the models can't do certain things. I will say Andrei Karpathy, I'm not sure if I'm saying his last name right, but he has a good mental model, I think, of thinking about AI, which is don't see AI as like supercharged human intelligence. Like, oh, it's just human intelligence being sort of bottled up and now a computer can do it. Machine intelligence is sort of like a fundamentally different kind of intelligence than human intelligence. He calls it an alien intelligence, not because it came from space, but kind of going to the root of the Latin root of that word, alius, other. It's a different kind of intelligence. And it's easy to get it mixed up because sometimes the outputs of machine intelligence look a lot like what the outputs of human intelligence would be. But the truth is, the way that the machine is producing those outputs is very, very different from the way that human intelligence does. Okay, wow, a little ramble in there. Okay, so we've gone over the reasons why whole word tokenization is not that efficient. The vocabulary list becomes too big. It's too many options for the model to choose from. It's bad with new words, and it doesn't let the model kind of like reuse the meaning of these roots that might show up in 20 different words. We talked about the downsides of character-based tokenization, which is even though the model only has a few options to choose from, and that's more efficient, it's really hard for the model to kind of compose meaning out of the characters, one character at a time. So the compromise that has been reached, and this is how most modern like tokenization systems are, is through sort of a combination of both. So yes, many common words will become one single token. And also the characters end up being tokens. But there's a lot of room in between where little composable chunks of words like un, and break, and able, they all become their own token. So the word unbreakable, rather than being one token and rather than being 11 tokens, will end up being 3 tokens. So here are the benefits to this approach. When you have tokens like this for these separate little like chunks, that means they become reusable. So this issue of break, right? The meaning of the word break just has to be in that word in that token for break, and then that token can get reused in many different places, like in the word unbreakable, in the word breaking, and the model isn't having to re-encode the meaning of the word break in all these different places. It just has the break token that gets combined with other tokens in meaningful ways. So that's really awesome. Another advantage of this like chunk approach, where like different chunks will have their own token, is for this new word problem, right? So now with this approach, if you give the model some big new word that it's never seen before, even though that big new word won't have a dedicated token, there might be chunks within it that the model can recognize. So the model has like a foothold on how to make sense of this new word you've given it, if within that new word there are chunks that the model can recognize. Maybe your new word starts with un, so forth. Okay, so this ends up being like the compromise that is in many systems now. And the way that these tokenizers are really interesting. So you might define up front, if you're training a large language model, you might define up front like how big you want that vocabulary to be. And how big you want the vocab to be might be a function of how many GPUs you have available, things like this. Like these are questions that really trickle down into the whole ecosystem of how a model gets trained and a model, the economics of the model. So like these aren't just like theoretical fun questions. Like this, there are very smart people probably getting paid like lots of money still thinking about how to improve this tokenization process because it matters a lot. And it's not like these things are settled either, by the way. These are not like settled questions. Everything that I'm going to talk about is an area of like active research and improvement. And as these AI systems get better and better and better, in part, that's going to be a result of all these data centers coming online. But in part, it's going to be down to improvements in things like tokenization and all the other sort of like processes and like algorithms that go into model training. They can get improved too, along not just the GPUs and how many GPUs you're throwing at it. Okay, now we can build on our knowledge to shed light on a few other things. So because of this chunking system where the most common words in the training data might get their own single token, but other long ones might be chunked up into 2 or 3, now we know why roughly 100 tokens in English usually amounts to about 75 words. And we also know, and this is very interesting, that you take this sentence, the weather is nice today in English. So this ends up costing about 5 tokens in English, right? Because each one of these words gets its own token because they're common enough in the training data that the tokenizer decided, okay, this word kind of deserves its own token. But in Korean, this actually ends up taking 11 tokens to express. And in Burmese, it ends up taking 25 tokens. Now, why is this? Well, it's because these languages are so much less common in the training data than English that a lot of the words that might be common in Burmese that in theory might deserve their own token, because Burmese is so much more rare in the training data, that it ends up that some of those common words end up not getting like tokenized into single words. They end up staying as like chunks or even characters, depending on how rare the language is in the training data. So this is this like English bias that people talk about with large language models, where they're much more efficient with English because of the prominence of English in the training data. Many more words in English have been kind of chunked into a single token because they're so common in the training data. So in Burmese, even though a word might be common in Burmese, it still might not have gotten its own dedicated token because it was so rare in the training data. Okay. Wow, amazing. Now, the one last thing I want to close on. So I mentioned that, an LLM might be bad at counting the number of R's in the word strawberry because it never sees the full word. It's seeing these 2 distinct tokens, and you're asking it to like count things between 2 different tokens. But even when it like sees the token, it's not like the model sees these individual characters. And in fact, every token at the end of the day, every token in the model's like token list ends up getting represented by just a number. And these numbers actually aren't that important from like a math perspective. They don't get used in math equations. The number itself is arbitrary. It just needs to be unique. Every token gets its own unique identifier. Think of it as just like a little like name tag for the token or something. It's just a unique ID for the token. So you might be wondering, well, and here's my little like table of tokens down here. You might be wondering, well, why does the token for able, why is it represented as a number in the token list, right? Why don't you just have like able there and un there and break? So the reason why every token gets its own unique like little number ID is because GPUs, which are the machines like used by these AI systems, GPUs just have a much easier time like navigating through this table to find the tokens they need if the tokens are represented with numbers, integers, rather than strings of characters, because these strings of characters just aren't that easy for the machine to work with. It's easier for the machine to look up a number and see what is in that token rather than to look up a string of characters. So this is sort of interesting, like right from the very beginning, right? These letters and words that we're used to, they really get, not only do they get broken down like into these tokens, but then the tokens at the end of the day are actually just unique numbers in a table. So yes, you know, the token 60 represents this token able, represents this like chunk able, but it's not like the model ever sees able. The model just sees 60 and then another set of numbers that represents what this token means, the embeddings. And coming up, we'll learn all about embeddings. Okay, wow. It's fine. I meant for this video to be maybe 5 minutes max. I'm probably at like 15 or 20, but I think I'm just going to go with it. If you're here to learn stuff, I think you'll stick around. I know not everyone will kind of join me on this journey, but for those that do, I think you're going to be in for a fun ride. All right, over and out.